record and let's share the screen. I'll put you guys. I have some work getting done on my house. Where's my little, oh, I guess only with 3 of you, I don't get to make it. No, wait.
What does P-type stand for?
Precipitation type.
Oh, duh.
So rain here, here's the rain and snow.
Oh, there it is.
Mm-hmm.
With only 2 of you, I can't resize my window. Why is that? Isn't that weird?
Maybe it's just the window to. Oh, the window with.
Yeah, when there's only
camera.
2 of you, right? I can't make it larger because your faces are usually big on my TV. Well, I guess you'll just stay on that screen. Okay, well, gosh, a class of 2, that kind of sucks, but I'm sure James will be here. By the way, Allison, you can talk to her when she comes here on Thursday. She got 100% on her test.
On her dynamics?
Yeah, it was like when she was the 3rd thermodynamics section or whatever, but got 100. Perfect score.
She was a nervous wreck.
Well, she's always a nervous wreck, but she's a really good student. She works. You know, the great thing about her nerves is that it makes her work. So you can congratulate her when you see her, but I thought I'd brag about her to you guys because she's very cool about that.
That's what, a 300 level course down there?
Oh yeah, that's a
junior level or
senior, maybe senior level. Okay, so I'm going to go to. No, I'm going to go to your grade center since you guys are the 2 that are here. View grade details. I'm going to view your attempt. So what problem were we on?
I think we were toward the end.
Yeah, we were just a couple left. I think we got the hardest ones. The rest ones are on the work and the engine ones.
I believe so.
So here's the hypsometric one. Well, actually, this is really easy one, right? You have an isometric atmosphere. You're using the hypsometric equation. You're given the mean virtual temperatures at different heights, and you calculate H. So pretty straightforward.
Yeah.
You got to remember that stuff. Here's Poisson's equation. You plugging that in. You got to admit it's kind of fun to be able to say what's theta, and you can just calculate it.
Yeah.
A couple of things. I also like that you can calculate the theta E, which is another thing that's fun to do. Now this next one was a little bit harder, right? Because but you break it down into different parts. And the very first thing you do is you solve for the virtual temperature, which you have all the information of, right? If you know the pressure, let me get my pens open.
Which one is this?
This is one in the worksheet.
Oh, yeah.
It's the last one.
This is the one that I made up so that you get an idea of a couple things on it. So, you know, you're given E and you're given P, so this whole thing is pretty straightforward to get the virtual temperature. And then over here, you're finding the density at 1,020 millibars. So we know the virtual temperature, we know the pressure, we should solve for the density. Okay, so we get 1.189. What is the typical density of dry air at the surface? Like the standard atmosphere, do you remember what that number is?
No.
Oh, let's try this again.
That'd be close.
It is 1.25 kilograms per meter cubed. So that is standard atmosphere density at 1,013.25 millibars. So if you realize that it's under higher pressure, but it's only a little bit higher than standard, so it'd be a little bit more dense, maybe 1.26 at the extra 7 millibars. But the fact that it's so warm, 25 degrees, and what standard sea level temperature? Like in a standard atmosphere, what's the temperature at the surface?
Is it 293?
288.
288.
Because it's plus 15. That's our average temperature. And then we have some amount of water vapor in the air, but this is a pretty high amount of water vapor with 6 millibars. So that's humid air. And that's why the density's a little bit less, but it's not that much less, right?
Is the 1.25, is that the molecular boundary layer, or is that substantially higher?
That is when the pressure is 1,013.25.
Okay.
So that's our standard atmosphere.
Okay.
That's how we define it on average. So if you look in the appendix in your book, you'll see that value for density of air.
Do you know offhand what the density is down at the molecular level, molecular boundary?
Well, it's going to be less dense than the air above it. So,
Yeah.
that's it would be cool to do a discussion on how much does it, like, you guys want to do something? You want to do something? You want to do something different and fun, just for the hell of it? Okay, so let's do this. Throw you guys back on here. Just for the hell of it, I'm going to try to do this. So I've got, let's say the pressure is 1,000 millibars. Okay, and we know that the pressure change over height is approximately, you remember what the relationship is? What? You remember what that is?
Oh, how many feet? Was it 7 or 8 feet?
Well, not in the molecular boundary layer,
Oh.
but it drops. Remember, when we look at the hypsometric, it drops about 1 millibar for every 8 meters.
8 meters.
So we know the change in pressure over height. Okay, so if at 1,000 millibars, the pressure is equal to the density times RD TV. Okay, and let's just say it is going to be, let's just make it easy, 288 Kelvin. Then what is the density at the surface? So P naught equals density naught times RD times TV naught. And what we're going to say is 1,020.00 pascals equals the density times 287, and I'm going to blah, 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 blah. And then the virtual temperature, 288. Okay, so go ahead and what do you get for the density? You want to just do that real quick?
$1.234.
Okay, 1.234 kilograms per meter cubed. Okay, now let's go up 1 millibar, 8 meters. So we have 1,019.00 pascals will equal, now we have to have a density that is more dense. Okay, so let's use, instead of 1.234, let's go use 0.135, just for the hell of it. Times 287 times whatever this virtual temperature is. So what would the virtual temperature be if the density goes up by 1,000th of a kilogram per meter cubed?
$287.49.
So the temperature, 287.49. Okay, so the temperature has gone down by how much? 0.51 K divided by 8 meters times 1,000 meters per kilometer. And what do you get?
35,936.46.
35, what?
936.
Right? 35, which would be degrees Celsius per kilometer. So there's your lapse rate in a situation like this. You know what? Do me a favor, just for my own well-being. Instead of this, make it 4 again. Let's go back to 4. So that becomes
287.72.
287.72, which means 0.28 divided by 8 times 1,000 meters per kilometer. What do you get there?
$35.
How close, how precise were you in here?
Pretty precise.
What significant digits?
I went out to at least 2. Should I go out more?
Yeah, do that first.
Okay.
Just for this last one, 1.234 is that one.
$287.7246.
46. Okay. So if I put those numbers in, then the difference would be what? 0.2754. Put that into there divided by 8.
Okay, hold on. $297.7246.8. 37.2155.
Oh, it's going the wrong way. Because what we have defined as the autoconvective lapse rate is 34 degrees Celsius per kilometer. So what I'm assuming is that the density, right, if I imagine the density versus height, this would be a line of constant density, which I think is an isopicnic or something. Constant density. So I'm assuming that if the density increases, it's going to be just more than whatever this value is. So we know that the value is supposed to be 34 degrees Celsius per kilometer. Then the question is, well, why did we get that? How do we know that that must be true? And when we were really precise, we noticed it went from 35.96, it went up by a whole full degree, and I really need to get down to 34. So where do you think the source of error would be?
It's in the density that you used.
Well, it doesn't matter because I'm using the same one.
Oh.
The error is probably in here. Right?
Yeah.
Because I said 1 millibar per 8 meters. So
I bet you.
Just for the sake of it, take 0.51 over 8 and make it over 8.3.
$61.4457.
0.51 divided by 8.3?
Yep.
Yep. So that's just making it even worse.
Oh, wait, I need to make this number smaller. No, what? Here, where's my phone? You have
63.7.
0.51 divided by 8 is 60.
0.06375.
How did you get 35.9?
Yeah, I'm just wondering too.
Yeah, that's.
Oops.
Because I probably should have tried it then.
Well, how did you get 37 over here?
Yeah, I don't know. What did I do?
Would 28 over 8 times the 1,000? It gives you 35.
Okay, wait, what am I doing here? Okay, well, hold on. For the sake of those watching at home, you should have been in class, so I don't really care. Let's try this again. Pressure equals 1,000 millibars. Temperature is 288. And we'll say virtual temperature just to make it easy. Okay, so what is the density? And we said it's 1,000. It's 12 divided by 287 divided by 288. Oh, well, first of all, that's a big different number too. 1.21 kilograms per meter cubed. So now we go up 10 millibars, or down. Let's just go down 1 millibar. 999 millibars. The density, we're going to say, is still 1.21 kilogram per meter cubed. What is the new virtual temperature now? And it would be 99900 divided by 1.21 divided by 287. And we would get 287.67. Huh. Well, something's wrong here, right? Because the autoconvective lapse rate is supposed to be, well, that's going down. So delta T is equal to 0.33. Actually, I can do degrees Celsius because it's the same thing. So delta T over delta Z is what the lapse rate is. I'm trying to figure this out. But I know that the change in height divided by the change in pressure is approximately 0.33 times 1 meter per 8 millibars. So it should be 0.33 divided by 8 millibars times this 41.25. Is that what you guys get? If 1 meter for 8 millibars. No, not 8 millibars. Oh, hold on. That's totally wrong. Totally wrong. What am I doing? This is 8 meters.
Per 1 millibar.
You need to convert kilometers.
1 meter, no, 8 meters per 1 millibar.
Millibar, okay.
Oh,
It is kilometers, isn't it?
well, yeah. Times 1 millibar, right? Because this is a rate. So this is how much I've actually changed. So the millibars goes away. And this is going to get me,
Degrees
oh, wait
per,
a second. Hold on. Oh, I see what I did wrong. Hold on. I'm doing a lot of bad algebra here. See what I mean about algebra? Being the curse.
Yeah.
So what is point? So I'm trying to figure out what, oh, see, this is the problem. I know what? I know that delta T is equal to 0.33 Celsius.
Per
I
1.
know that delta Z over delta P, or is it the other way around? No, it's delta P over delta Z is equal to 1 millibar per 8 meters. If I multiply that what do I get?
Well, it's delta T over delta P, isn't it? Because we only changed by 1 millibar as well.
Right. So, but what is this? It's degrees Celsius, 0.33 degrees Celsius, divided by 8 meters times delta P, which we said is 1 millibar. Because I don't want the delta P in there, so I have to divide by 1 over delta P. So it should be 0.33 divided by 8, right?
Gets you that
41.25
0.25. Yeah.
degrees Celsius per kilometer. Okay, now the autoconvective lapse rate is supposed to be 34 degrees Celsius per kilometer, which says that the atmosphere will overturn, which means it means this, right? How does density change with height? It's greater than 0. So what would make this a value of 32? Well, let's go 0.33 divided by something is equal to 34 degrees Celsius per kilometer. So 34 divided by 0.33 equals 100. Divided by 1,000. What am I doing? Do you know what I'm doing? I'm getting confused here.
It should be.
I want it to be 34. I got 41.25. So that means 0.33 divided by what is equal to 34. So 0.33 divided by 34 times 1,000 is 9.7.
7. Mm-hmm.
Okay, so to get this, delta P would have to be 9.7 meters. And we said it was 8. That's probably where the error is. So let's see. Let's take a look here. Auto convective lapse rate. 34.2 degrees. The density of air is constant with height when that's the rate. So now how do we get that rate exactly? Oh, they use the hydrostatic equilibrium. P equals RG. What's RG? I'm assuming that's just an ideal gas constant. Times the density of Z. So density is, oh, well, that makes sense, right? We had dP dZ over here of, oh, equals minus rho G, right? I should have known that's the hydrostatic. dP dZ equals minus rho G. Well, I know the density, which is, what did I say it was? It was 1.21 kilograms per meter cubed times 9.8 meters per second squared. So what is this? So if I do that, 1.21 times 9.8.
11.858.
11.858. what would the unit be? Well, that's what it becomes. So, oh, this is way better, huh? dp dz equal, and then what does g, what do they put in here? How did they go from here to there? They're saying that the pressure is, no, the density is minus 1 over g dp dz, which makes sense, which is equal to rg over g. Oh, so they took the derivative of this side, which is product rule, t dp dz plus p times dt dz. Oh, beautiful. Thank you very much, NASA. And then you solve for dt dz. But t and p rho are always positive, so that when so the autoconvective lapse rate is g over r 9.8 divided by 287 times 1034.15. Oh, that's good. Let me do that so that it's more neat. Are you liking this?
Yeah.
I kind of like stuff like this. So the hydrostatic is dp dz equals minus rho g. And we said that rho, in this case, will go 1.25 kilograms per meter cubed. And we know that gravity is 9.8 meters per second squared. So and I want dt dz. So what do they do? They go, well, but pressure is equal to rho rd tv. Right? So the derivative of rho times rd times tv all over dz is equal to minus rho times g. Does that follow? Now I have three things in here to take the derivative of. RD can come out. What about density? In order to do this, what are we claiming density to be? Remember we drew that little graph here?
Constant.
Height, density, so density is constant. So I can go rho RD times the derivative of TV dz, which is the lapse rate, equals minus rho g. But rho's cancel out. And RD comes over there, and I'm left with the derivative of temperature with respect to height is equal to minus g, where the minus is just because it's a lapse rate, it's already cooling, over RD. And if we use 9.8 meters per second squared divided by 287 joules, which is a kilogram meter per second squared per Kelvin per kilogram. I look at this and I go, well, the kilograms cancel, the meters cancel, the seconds cancel. There's an extra. I made one mistake here. This is a joule, which is a kilogram meter squared per second squared. So one of the meters canceled, and I'm left with 9.8 divided by 287, which is 0.034 kelvins per meter, which is equal to 3.4 kelvins per kilometer, which is, oops, not 3.4. Which is the autoconvective lapse rate. That's a much cleaner way, isn't it, than fooling around with that? I knew there had to be some way to do it. Boy, that kind of makes me happy. I hope you like that.
Yeah.
Makes more sense. Yeah.
It's cool, isn't it?
Yeah.
Mm-hmm.
Now you understand why this is. And of course, this is the virtual temperature, but given the molecular boundary layer, right, there's not a whole lot of difference in the water vapor because it's so turbulent and mixing that, you know, you definitely can get a little bit of water vapor, and that will change your RD, right? Or that'll change your virtual temperature. But it's just your virtual temperature change, so it's really not that big of a difference. So that, it just says when you heat that, then the air auto-convects. It mixes automatically. Well, I don't know about you, but I thought that was kind of fun to do.
That's neat.
And now you know more about the autoconvective lapse rate. So think about this. You're going to be, Nick, you're going to be a junior, and you can derive what the autoconvective lapse rate is. And there will be people in grad school who've never even heard of the autoconvective lapse rate.
All right.
Remember, you dominate them. That's what you should do. Always dominate other people. Okay, so let's go on here. So we got to this point where we were looking at density. That we just kind of went off. Now, what here is you want to define delta Z. So in order to do that, you needed to come up with, given this information, you had to talk about what the hypsometric, which H was. Okay, and you got H is 7.29. Now, why did you say 7.29?
My guess is I probably pulled that constant from the book.
Okay, what you should have done is in here. Now, I give you full points because I thought you did a great job, and that's what I'm looking for. It's not perfection, it's just progress. I want you to turn to page 69.
$327.
Yes, but what did I give you in the information? I gave you temperature is 298 at the surface. I gave you the pressure, and I said 500 millibars is at 5.3. So really, you're going to use 3.25. Because you want to solve for H. So you've got the changes in the heights. And really, I should have said G of potential height, but. So I know that it's at 5.3 kilometers. So delta Z is 5.3 kilometers. Then you take the natural log of 1,020 and 500, and you solve for H. So go ahead and do that. You need 1,020 divided by 500, and then you need to take the natural log of that, which is 2.04. 0.7129.
Right.
How do I flip that? 0.7129, well, whatever. 5.3 divided by 0.7129 is 7.43. So that's what your H should be.
Okay.
So you should have used equation 3.25 to solve for H. Now, you may have just used equation 327 because what did you use for T? You're like, what's the value of T that you should be using?
298?
No, because T is the mean temperature of that layer. And you use the surface temperature. So really important that you look at equation 3.27 is that's assuming a what atmosphere?
Standard?
No, look at the top of that section for a
Isothermal.
right? It's not isothermal.
Right.
So
Oops.
that's why you're going to get a different value. So you want to remember that you're assuming an atmosphere where the pressure decreases exponentially. That's what you're assuming.
Mm-hmm.
So that's how you figure out what the H would be with that drop in exponential drop. Then when you go into the density stuff, you use the same thing. And the only difference here is, again, you're going to use that H that you just calculated. Because you're assuming that density drops exponentially with height. So you'd want to use equation 3.25, but instead of pressure, what are we going to use? You're going to use density because
Density.
the same thing is true. We're assuming that, you know, one of the things that you need to remember is that, hold on, if you have this equation, right? We have that equation. That's 3.25, which is just the expression of that. We are saying that pressure, all this means is pressure drops exponentially. But watch this, guys. Are you watching the screen?
Mm-hmm.
Mm-hmm.
Screen. I can do this. I can put in density instead of pressure and get the same thing because I'm assuming density drops exponentially.
Oh, okay.
So you can use the same equation that you did, which is what you did, right? That's what you have right here. The only thing is, instead of using 8.55, you should use that 7.434, which is what we did.
Yeah.
So it's just the value of H that is not correct.
Okay.
So in a perfect world, I would have just said, that's all.
Okay, so technically there then, since it was isothermal, that you had to solve for the scale height then.
Correct. Because you don't know the
Okay.
average virtual temperature. But
That
you
makes
do
sense.
know the fact that pressure and density are both decreasing exponentially. And that's the reason we get to H. And the funny thing is, we get to know what that value of H is by what the temperature is, which says how steep of an exponential curve is it going to be. Fair enough?
Yep.
Mm-hmm.
Okay. Moving along. We did those. We did this. You know, one of the things that I hope you get is the idea that doing problems is exciting when you work on it. I mean, look at the stuff we did with the lapse rate. And this is what I want students to get is realize that you have the ability to do it. If you're confident, it's very Yoda-esque, right? It's not that you can't do it, it's just that you haven't done it yet.
Yeah.
But you have everything you want. So we did the isothermal compression one. We did this one in class.
Yeah.
We did
341.
we did this one.
Yeah.
We did that one. That's for the
I think 58 is where we stopped.
58, right? So let's look at 3.58. An ideal reversible engine has a source and sink. Okay? So it has a source of temperatures of 100 and 0, and it's receiving 20 joules of heat for every cycle. Okay? And all you really need to think about is just figure out the joules, 20 joules, multiply by 10 at the end. Okay, so oh, this is interesting. This is interesting that you did it this way because I don't think you needed to. But you just said that the efficiency, right? What Greek letter is this?
That's a stylized N.
Yeah, but what's the Greek letter?
Yeah. Hold on. I gotta get the cheat sheet. Eta. ETA.
So that's eta.
Not the model.
Okay, so eta, efficiency, is Q1 minus Q2, which we know is T1 minus T2 all over T1. You know, or if you wanted, you could go 1 minus Q2 over Q1, and that's going to be Q2 over Q1 is just 1 minus T2 over T1. All over that, so you kind of prove that. So we got that. Then you said we know the temperatures. We go the efficiency is 0.268. And then here it's just simple. The efficiency times the amount of heat that you draw in is your change. So that really, you could have just done that. You could have said work is Q in minus Q out. Which we know is that's what you have over here, right? And so we say 20, we know the efficiency, we get 5.36 joules. That's the work. Just remember. So kind of this engine with an efficiency of 0.268 says we get 5.36 if we are drawing in 20 joules. Or we're drawing in 20 joules of heat from the source. So good. That's a good problem. Here we go. And that's how much heat we're putting into rejecting to the sink in one cycle. Good work. Hey, hold on a second, guys. Let me go get a cup of coffee. Hello, this is Paul. Man, it's kind of pretty outside, I must say. I would prefer this snow. I would prefer this snow all year to actually accumulating snow. Just it can snow and it's pretty. So, all right, sorry. Thanks for letting me get coffee. Okay, the last one. Is this the last one? Oh, it's a refrigerator. Were you able to get this one, Nick? 3.59.
An attempt on it, but I'm not sure if I did it right or not.
So a refrigerator is an internal temperature of 0 and is situated in a room with the steady temperature of 17. The refrigerator is driven by a 1 kilowatt motor, and it calculates the time required to freeze 20 kilograms of water already cooled to 0. So the only thing that you need to think about is I've got to take out X amount of heat. So remember, what does a refrigerator do? Like, Nick, how would you say, what does a refrigerator do?
Technically, what it does is it uses an engine to expel excess heat within the actual refrigerator unit, right?
Yeah, there's a better way to describe that, though. What does an engine do? Like, in simple terms. By the way, I'm
Does
going to
work.
be talking. By the way, Nick, sorry, I'm just going to interrupt. By the way, I'm going to be talking about this big final project. This is the kind of stuff that I expect to see in there, like lots of different ways of expressing something. So, what does an engine do, Nick?
Does work, releases heat. A little bit more.
Yeah. This goes to the mechanical universe description, which I thought was good. It takes heat from a warm source and transfers it to a cold source, a cold sink. So I'm taking heat from a warm area and pushing out heat into a cold sink. So what does a refrigerator do, which is backwards?
Opposite.
It takes heat from a cold source and it puts it out into a heat sink. It runs it backwards. Mm-hmm. So I'm withdrawing heat from the refrigerator and I'm putting it into the air around me.
Mm-hmm.
Okay, so I need to get my stuff up because there's two different ways. I think there's one. There's two different ways to solve this problem. Jim, you want to kind of talk through your method?
Okay.
What you thought about?
Calculated the efficiency.
Which is, that's a nice cheaty, not a cheaty way, but it's a nice basic way to kind of go there right in the beginning and say, all right, let's do with this stuff. Let's just do the efficiency stuff because we get nice equations from that.
And then once I got that, I rearranged the equation such that create a relation as to how much energy would be taken from the H2O per every Q2, per every temperature change in T1, or in Q2, Basically calculated the efficiency using temperature, then equated it to the energy, Q1 over minus Q2 over Q2, and then rearranged that to determine what the energy change was per change in Q2, and that's a ratio.
So you've got a video of this. This would be a good one to do. I'm going to show you two ways to think about this. So what am I trying to do? I mean, I could use entropy for this. What's the formula for change in entropy here? Which formula for entropy would I be here?
God.
The equation on 101.
Well, no, I could. Yeah. Which is really, okay, which is really the equation on 3.84. So if I go to 3.84, but yes, you're right, that ds is equal to dq reversible at a t.
Yeah, it's
Right.
just solved.
So-
That's solved.
So I'm saying that the ds is going to be what? What is this term? This is the heating term. Well, what heat am I talking about? Now you go to page 101 and you understand that the heating is going to be the mass times the latent heat, but I'm melting it. I mean, I'm freezing it, so that's the latent heat of fusion, divided by the temperature, which is 273 Kelvin. And then we know, you know what I'm going to do? Just, I know I don't always want to do it this way, but I'm just going to say that we know the mass is 20 kilograms. We know the latent heat of fusion is 3.34 times 10 to the fifth joules per kilogram, all over 273 Kelvin. And so we get 2.45 times 10 to the fourth joules per degree. That's at 273 K. That's, okay, do you see what that answer is?
Mm-hmm.
Now, there is another way of looking at stuff. Is that entropy is conserved. And so I use the same concept of, where's the best way to show this? If I use the same formula and I go, well, this is going to be 2.45 times 10 to the fourth joules per degree times 17, because that's the change in the temperature. Then I get 4.165 times 10 to the fifth joules.
Mm.
So that's how much, that's the heat we're putting into it when the temperature is changing. Now, the engine needs to generate this much heat and how much it's a kilowatt, which is 1,000 joules per second, times 1 minute over 60 seconds is equal to 6.94 minutes, which is what you got, right, Jim?
I left it in seconds, but hold on. I got 414 seconds. You got, it converts to 416.4 seconds.
So about the same?
Yeah.
Okay. So this is using entropy to solve that problem. And that would have been one way of dealing with it. But I have a really cool second solution, which is actually much closer to what Jim did. So I want you to think about what I've done here. I've used this formula for the same thing, saying that I'm using T to be 17. It's kind of a weird thing that I did. But let's do this one. This is kind of fun. Do you agree to this?
Okay.
Here's the refrigerator. There's my box in the refrigerator. And here's a thing of ice in the refrigerator. And the temperature here, we're going to say is T2. And the temperature out here is T1. We know that T1 is 17 Celsius. Okay, which is 290 K. We are extracting heat, which is Q2, and we're putting it in Q1. So Q2 is the amount of heat that we need, which is what we calculated before. It's L times the mass. That's how much heat we need to put in there to freeze the water.
Okay.
So Q2, and I'm not going to write the whole numbers out, comes to be 6.68 times 10 to the 6th joules. That's how much heat you need to melt to freeze the ice. Sorry, that's how much heat you need to extract.
Mm-hmm.
From here, Q1 is equal to Q2 times T1 over T2. Well, this should be pretty easy, isn't it? 6.68 times 10 to the 6th joules times 290 over 273 is equal to 7.096 times 10 to the 6th. The work is the heat in minus the heat out, which is the difference between that and that. And for the sake of time, I'm just going to give you the answer, 4.16 times 10 to the 5th joules.
Which is the same answer.
Same answer.
The same answer you got the other way.
I like this one. I think this one is one that you can understand what I'm doing. Because when you look at this picture, right, I'm at temperature T2, at a cold temperature, I'm extracting heat.
Yeah.
And I'm putting heat into T1.
Yeah.
But to show you how cool this whole thing with that entropy is, let's watch this. The work, you know what I'm going to do? Just for the sake of being cool, I'm going to use a different color. The work is Q1 minus Q2, right? I hope you understand that.
Yeah.
Mm-hmm.
But based on this equation here, that's going to be Q1 minus Q1 times T2 over T1. I'm solving for Q2. T2 will be up on the numerator, T1 in the denominator from this equation. Does that make sense? So if you're looking at this in the future, you can kind of think of it this way. Oops. That is how we get here.
Okay.
But the work is Q1 times 1 minus T2 over T1. The work is Q1 times T1 over T1 minus T2 over T1. You follow that so far?
Yes.
So what's this? The ratio of heat to temperature is what? The ratio of heat to temperature is entropy.
Entropy.
So really, you could have figured out how much work is required simply by knowing the entropy times the difference in temperature. But when you look at my first solution, that's what we did.
Mm-hmm.
The entropy times the change in the temperature. We
Yep.
know the change in temperature is 17 times the entropy. And entropy, according to that equation, is latent heat times the mass divided by temperature.
It's interesting that the way I did this equation in the previous, I used efficiency.
Yep. And all you did is you had that extra term in there because you didn't, but you got the right idea. You could have just simplified out, instead of using efficiency,
Yeah.
the idea of what work is.
But using efficiency kind of hides the details as to physically what's going on.
Exactly. But
and now I can see where my bias came in.
But it's fun because what you're doing is fine. And the more that you do stuff and the more you see different routes to the same conclusion, the more that you'll understand what's going on.
Yeah. Yeah, I can see we're using the efficiency of something hides a lot.
But it's not wrong, right? That's what
Agreed.
we know that works from it. So
yeah, but once you know what's going on, then using efficiency is fine. But trying to connect the math with the physical, the efficiency kind of obfuscates what's going on.
If you're going to do well in thermodynamics, and this little proof here, and then the final conclusion of this, I think this is super important that you kind of keep this in mind. That's a really clever way of getting to it.
Yeah.
Because you can solve a lot of problems this way.
Cool.
So hopefully you like that. I thought that was a fun thing to do.
Okay.
Then the last problem. Oops, I'm gonna get. What did I do? I'm gonna get in here. We'll get back to it. And we'll go all the way to the end for the last problem, which is actually a great problem because all you're saying for this problem is that you're going to change entropy. And so I'm going to let you take a look at what he's done because it's all fine. Oops, not this one. You're changing entropy. And so you change entropies two ways, changing the state or changing the temperature.
Right.
So look at page 101. And the first one is we're integrating CdT over T, which is going to get logarithms. So that's assuming the temperature is changing. So that first delta S of water is when you change the temperature of water. That's the formula you use. You need to use the specific heat of water. If I were using air, you'd use the specific heat of air. But water is the one that we're typically doing. And we know C, and we get a joules per kilogram, or per Kelvin. A joules per Kelvin is an entropy. Joules of energy over a temperature. And if you are going to change the entropy by changing the state of a gas, then you use the one that we just used, L, mass times L, the latent heat, divided by the temperature where that's taking place. So what Jim did here is you just break it up into 4 parts. 4 parts. And the one of them is to raise the temperature from 263 from -10 to 273. You raise the ice, the specific heat of solid water is 22106 of ice. And then we get 0.1572 joules per Kelvin. Now think about that. How much entropy changes when I'm raising the temperature of ice? Hardly any. That's what you have to think about. Then I melt that. And now I've got...
I look at it differently. My chemistry says we're changing state from solid to liquid.
Solid to liquid, right. And that change of state has a huge change of entropy compared to raising the temperature of ice. Which it makes sense, right? When you're heating ice, are you really changing the structure very much of the water?
No.
Right? The crystal, the entropy, the order of it. So you don't have to do that much entropy change.
Well, you're staying in the same state.
So now you get 2.4 at 2.45 right in here. So that's a dot, not a comma, unless you're in Europe.
Right.
Over here, then now you're going to go from 0 to 100. Now you're taking water and you're heating it to the boiling point. And now you get 2.6. It's a lot of heat going into there to make that temperature go up. And then when I go from liquid to vapor, look at the entropy increase. Talk about an entropy increase, which comes out to be 12.06. You add them together and you get 17.3, or depending on how many significant digits you put in there. But this, see, if I were to give you a test, I'd give you one just like this, because that's straightforward. You should be able to do things like this. But if you think about it in terms of entropy, changing the structure of ice by warming it, very little change in structure, in randomness. Then when you melt it, you get a pretty significant change, which is the equivalence, almost the equivalence of raising the temperature of water 100 degrees. And think about how much heat you have to do. How much heat do you have to put in there? To melt water, 2106 joules per kilogram. To raise the temperature, I need to put in an order of magnitude higher, times 10 to the fifth. 2 orders of magnitude, 100 times. So you get this huge increase, equivalent of increase. But then, now I'm putting in 4,200 joules per kilogram to make that water evaporate. That's a lot. That's good heat, and I'm getting a huge increase in their entropy. So the term, when I look at these parts here, this part here is the dominant term in terms of entropy, because we're going from warming crystals, to water, warming water, to vapor, which is highly chaotic. And we use entropy to explain that. And I think that's cool. I think that's a good explanation of entropy.
Okay, that makes sense. It makes
We
a
do
lot
have
more sense.
Okay, that's a good one to do. And I think we've already done this one.
Yeah.
So there you go. There's our problems. There's our unit. We closed the unit today.
We did 3.62 already?
Yes. That derivation, where I call the stubborn method, we went over that in class, and there was a cleaner way to do that I showed in practical method number 2.
Okay.
I think I sent that out, as a matter of fact.
Right.
Oh, yeah, I remember that now.
Can I make a comment on 7.1?
What? Chapter 7?
Yeah, what you had us read?
Yeah, go ahead. Go ahead, Nick, turn to chapter 7.
Mm-hmm.
Could they have obfuscated the description anymore? They used a completely different terminology than what is typically used in math.
Exercise 7.1?
No, section 7.1.
Oh, okay.
Yeah, they introduced natural coordinates S and M, but in math it's TK or TN and K. For tangent, normal, and K.
Tangent. Yeah.
And
Well,
I thought
that's what goes on in the natural coordinates when you start looking at tangents. So that's the streamline function. So in table 7.1, that's the streamline function.
yeah. I just didn't.
Before we go into that, I do want to take a look at what I put online, which is your assignments.
Okay.
Okay, so here's your overall objectives for this meteorology program.
Oh, I didn't see that.
So I just put that in yesterday.
Okay.
And here's what the assignment is. Things meteorology majors at COD ought to know. And I don't know, there's 20, I don't know what we got, 20 something. So what you're going to do, when you leave here from COD, you're going to become Nick, you're going to become a junior, right? Mm-hmm. This is what I expect you to know, and I expect you to know it really well. Like, this is your lifeblood. So what you're going to be doing is you're going to be putting together sets of notes over these concepts. Now, the Bergeron process is stuff that we have gone through. We go through it in 1110. We go through it in 1119. It's in here. You can do that, but I expect you to do that on your own. Bayes-Bell law is going to be limited. That's just simple stuff. Chinook, Santa Ana, katabatic winds, that's independent. This one we have done in class. Cloud types, that's something you should know, right? I mean, you can do independent research on cloud types, but I want to make sure you know it. This is like a total thing. Now, this one here, conservation of angular momentum, do not do that yet, because we're going to be talking about that in huge detail, ways that you've never thought about it. Poisson's equation, we have done. Energy cascade, facts about the geostrophic wind are things we're doing in this upcoming unit. Geostrophic equation, gradient winds, and even to some extent hydrostatic, we're going to be doing. For laws, we've done. This one, you just need to know what I'm talking about. I've done I do this in 1110. We also do it in 1111. Hypsometric, we've done. Ideal gas law. Instability, we do in a lot of different courses. We've talked about absolute and conditional. We talked about it in here. We will be mentioning a few things about that. I might even do that today. Jet streak, we use this in, we talk about it. We talked a little bit already in this class, and we talk about it in 2115. This is just something you have to figure out on your own then. But we've talked about this many times. Mass continuity, this is stuff we are doing. Newton's 3 laws we talk about, but we're going to go into more detail. This one, the QG omega equation, I am only looking for qualitative. We will do that in this unit. Rayleigh scattering, why is the sky blue? We do that in 1110. We showed it a little bit in the me scattering. We talk about that. So I expect you to talk about Rayleigh versus me versus geometric optics. I want you to do this one. Land sea breeze circulations, we do that in a couple classes. Station models, come on, that's easy. Stefan-Boltzmann law, we have talked about that in a couple of classes. I think we talked about that in 1111, 1110. That's one you need to know. This is in the book also here. Thermal wind. We will end the semester with thermal wind. Thermally direct, indirect circulations, we've mentioned a number of times. We will talk a little bit about it during this class as well. Thermodynamic diagrams we do in other classes. You need to know that. We've talked about it here. 3-cell model, we do that in 1110, 1111. Virtual temperature, we've done. Green's displacement law, we have talked about in other classes. So the stuff that's in the squares are the ones that you should do last because we're going to be talking about in class. Everything else you can work on. Now I'm expecting, I said in there, I think it's about 2 to 5 pages.
Per topic.
Per topic. Now obviously, there's going to be a limit to how much you can talk about the Weisbach law. Because that might actually work with geostrophic and gradient winds. Those will be more. Hydrostatic, there's a lot of derivations we've done that you need to write down and put into your notes. So you're summarizing your notes from these classes into this stuff. So this, remember, this is in lieu of a test. I'm expecting lots of work. Now, I've had people that have been well over 100 pages. Margot, Nathan, a guy named Noah. I've had just some really great things. I've had stuff that's been less than 20 pages. What do you think this grade is? Right, that's not going to be a good one. This is going to be the stuff I'm looking for. You've got to use diagrams. You've got to use calc. I expect you to use calculus equations on some of these things. I don't want algebraic terms. I mean, you can put them in algebraic terms, but I want it in calculus terms. And that should do it.
And that's probably going to be due by...
That'll be due this Sunday, right before finals week.
Okay.
13th of December, I think you had it.
But this is not something that you can, I want you to pretend that we're having a midterm. And that's what you should get all the stuff done. Because, and to be honest with you, I think this will be more useful to you as you go forward in your career. So because it's such a small class, I don't need to test you guys because I already know grades. Tests are to give me grades. This will be more important to you, I think. And Jim, somebody like you, right? This is like, wow, this is a nice, concise.
Yeah.
Okay.
Okay. The thing that I wanted to talk about before we go on, and it deals with instability, is this. Okay, so here's the ground. In terms of potential temperature, what is a statically stable atmosphere? And what's the answer?
The dry lapse rate is greater than the environmental lapse rate.
Okay, so you could say this, right? I mean, I'm just reversing the way you said it. That's fine. But what about
Yeah.
using theta? A line of constant, on the dry adiabat is an isentrope. Isoentropy. So how would I write that using calculus? What's the value doing as I go higher? What's the value of this state, isentrope versus that one?
Getting larger.
Larger.
Okay, so that's a statically stable atmosphere. Theta increases with height. So imagine that I'm looking at isentropic surfaces. I'm looking at the cross section of an isentropic. Oh, let me do this. I'm looking at the cross section of an isentropic surface. And I'm saying over here, it's 283 Kelvin. And this would be 293 Kelvin. Which is warmer?
Which is warmer? B.
I think it would actually be A, wouldn't it?
Well,
If the
273. Because I guess if you imagine just the way I'm kind of thinking about it, if you put like a value of theta through B, that value is going to be, let's say 273. A is going to be in between 273 and 283, which is greater than what B is.
okay.
That makes sense.
Let's just do it this way, right? What would the temperature at A be if it's 10 Kelvin or it's 10 degrees Celsius there? What would it be? Wouldn't it be 16? What would it be here?
Oh, you changed it.
right? Because if I put a box there and I bring it down 1.5 kilometers to the ground, assuming the lapse rate's the same in both places.
Oh, okay.
Oh, okay.
But what if the lapse rate's not the same in both places? So let's think about this again. Let's go to a different example. Let's go to, let's imagine the lapse rate over here is 6 degrees Celsius per kilometer. And the lapse rate over on this side is -2 degrees Celsius per kilometer. What's the temperature at B now?
-3. Or
Would it be 7?
yeah, 7.
Because it's going to go up. And what would it be here? Still 16. So which is warmer?
It's 8.
The reverse. So when I ask you the question, where is it warmer? The answer is you don't know.
No.
Because what determines this is the lapse rates of these layers.
So we're looking at things in the synoptic. Can you really see that? Or oh, wait a minute. Would you be looking at a QT in order to figure this out, or something on a larger scale?
You'd have to be looking at soundings, but you're looking at an isentropic coordinate system.
Okay.
And you're saying, so here, so let's try this scenario. Here's your ground. And then let's try this one. Temperature is the same. Temperature at A equals temperature at B. That's a theta. Which is more stable, A or B?
B.
You know, let's say it's 283. I have to go to the same temperature, but I have to go further.
Further.
Mm-hmm.
Which means I can't be warming up as quickly.
Oh.
Which means this is the lower lapse rate. So the lower the lapse rate, the more stable. A is, or no.
Okay.
A has greater static stability than the atmosphere at A. So, does that make sense to you?
Yeah.
Mm-hmm.
Okay, so now we try this. Now we take the ground and I look at so this would be theta 1, theta 2, and we know that theta 2 is greater than theta 1 because we're assuming it's increasing. Only in an absolutely unstable atmosphere does theta increase or decrease with height. The closer they are together, what do we know? The closer these things are together.
Their lapse rates are closer.
I don't know what you mean by a lapse rate being closer.
Well, okay, then I'm going off in the wrong way.
No, you're fine. I don't know what the word closer versus lapse rates are.
Well, the two, oh, never mind.
If they're closer together,
It's a
That means-
more stable. Yeah.
the closer they are together, the more stable. So the more unstable, the further they are apart. Tell me that's cool.
It is kind of cool.
Let me show you one thing. Go to our analysis page. Isentropic maps. This is 305 Kelvin. That means every place on this map is the same temperature. Same potential temperature. And then the lines are telling me how high, well, not height, but what pressure do I have to go to reach that pressure. So over here, I have to go to 550 millibars to reach 385 Kelvin. Here, I have to go to 750 millibars to reach that. Right?
When you look at a map like this, why don't you call out theta AC? That would seem to be, knowing where that is would seem to be important.
With theta, what do you mean, AC?
Theta AC, areas of autoconvective.
No, because autoconvection is only giving a few lowest meters. This is the full atmosphere.
Okay.
So when I see these lines packed together,
Like at the base of the low trough?
well, like here, let me see if I can do this. So we know that there's instability out here, right? This is Cape.
Okay, you got MLK. Okay.
There. And where we see this, when these are spaced out, here, we're saying air. Think about what's going on here. The air is traveling this way at some 305 Kelvin. Okay?
Okay.
And then what is it doing? Oops, let's use yellow, sorry.
1042 pull.
Yeah, okay, I'm almost done. What's it doing as the air travels this way? It's going from 850 to 825 to 800 millibars. So what's the air doing as it crosses these lines?
It's sinking.
No, I'm going from 850 to 825.
Oh, I'm sorry. It's
going up.
So this is where there's isentropic lift. Air is rising in this area. What's going on over here? Air is traveling. Hold on.
the other way.
What's going on here? Air is ascending.
Ascending.
Because I'm going at that pressure contour, I'm going to higher. To get to that temperature, I have to go to higher pressures.
Right.
So this is just another way of visualizing the atmosphere in terms of isentropic coordinates. But understanding that isentropes and stability are related. One of the cool things that we have also is we have this product. We have cross-sectional analysis.
Yeah, I've looked at these. These are,
So if I want to go Corpus, let's go Del Rio to Bismarck. I get theta, which is in the red. And again, you see now the vertical, it's fairly stable here. It's most unstable. We can, and this is not a really good example, but we can find where they're furthest apart is where the air is least statically stable. So that would be in this area here. We can do the same thing with theta E because now we're dealing with that. We do this in meso. This is where the air is very unstable. We have some convective instability in this area. And if I go back to where that is, if I go back to where that is, I'm looking down here someplace.
why are the stations picked?
SPC
where they are?
has got thunderstorm risks in that area.
Go back to the product. Yeah. Why are those stations selected and not possibly any station?
Because we're generating images and this is all we're generating.
Okay.
We're not generating on the fly. That might be something worth doing, but we're trying to see across surfaces in the central US. If I want, this north-south one is pretty cool. I could have done.
I would think the stations that would be like from ILN to GRB, those would be a specific interest for severe weather.
Well, I can get stuff like this. Again, I'm just trying to visualize some things.
Yeah, okay.
It's a little bit harder to do this one as a whole, but. Okay, well, guys, I'm surprised there's only two of us. I don't know where the rest of you guys are. I mean, I know where Mike is, but I've only gotten assignments from you two. You guys gotta keep up. I know it's tough, COVID world. If you need to talk to me. You two are doing great. So I will see you guys on Thursday.
Okay, sir.
Okay.
All right. See you then.
Bye-bye.
Bye.